Greetings to everyone in the audience. My name is Szalay. I'm from the local high school of Radnó, the Experimental High School. I've been fortunate enough to be awarded this prestigious award this year and get the chance to give this presentation. In 2021, I had the chance to conduct research at my own high school. Me and my team of 23 other high school students, with the encouragement of our teachers and counselors, decided to test ourselves at the international iGEM competition. As our topic, we choose cancer screening, cancer diagnosis, and wanted to somehow contribute to this field of science at a high schooler level. In my presentation, I will briefly discuss the state of cancer research and cancer screening in Hungary, our team's project, how it works, how we prove that it works, and lastly talk about its future potentials. So, although multiple screening methods are widespread in Hungary, they are quite popular. For example, colon and lung cancer screenings are widespread. Still, every fourth death in Hungary is due to cancer in some form or another. This is largely due to the fact that less common cancer types lack widespread screenings, and the fact that it's hard to get the masses, the people, the average people, to participate in these screening actions. Of course, the most obvious answer would be to have more people, to encourage more people to partake in these screenings, and to have methods for less common cancer types. A possible route when diagnosing cancer is to look for biomarkers, so-called biomarkers in body fluids. For example, microRNAs. This is what our team used. These are 15 to 25 base pair long single-stranded RNA sequences which can be found in body fluids, and they can be cancer-specific markers. This is what our team worked with. It is important to establish that when working with RNA, the most important step, the most crucial step, is to somehow stabilize it. Otherwise, it is impossible to detect the trace amount of RNA that is present in the body fluids, even when their concentration is increased by 100-fold due to a cancer. Our team used microscopic scale magnetic beads to which single-stranded DNAs were attached by their 3' end. These single-stranded DNAs were specifically designed for the RNA we wanted to detect, in the regard that they have a region which is complementary to the RNA we want to detect. Thereby, the RNA can hybridize to them and forming this double-stranded region. This double-stranded region allows for our methods, our products' most important feature, which is the RNA signal's amplification. This is needed because we need to amplify the signal in order to be able to detect it. We achieved this by using a mixture which had a lot of different enzymes in it. The first, which is the most important, is DNA polymerase. The RNA which bound to the single-stranded DNA formed a short double-stranded region, and this can be used as a primer by the DNA polymerase enzyme, just like during DNA synthesis in the cell. The DNA polymerase completes and makes the whole sequence double-stranded, including the T7 RNA polymerase promoter at the end. It is important, this specific enzyme is important, the T7 RNA polymerase, because this is a type of RNA polymerase which can only recognize this double-stranded promoter. In the context of our project, this means that it can only perform its function when the RNA we want to detect is present in the solution, making the screening effective. The RNA polymerase can begin its function, and it starts to synthesize RNAs based on the information coded in the DNA. This is something we can influence because we designed the single-stranded DNA, and we know the sequence of this amplified RNA. Even though thereby we amplify the RNA signal, this still would not be enough to be able to detect it. We need to further amplify it. We achieve this by having also single-stranded DNA attached to magnetic beads, but this time they have specific region, complementary region to the before amplified RNA, thereby repeating the whole process and further amplifying the signal. This higher concentration of single-stranded RNA in the concentration is what we detect. We used intercalating dye, cyber-green intercalating dye. This is a dye which can bound to single-stranded RNA and thereby become fluorescent. This is what we used in our experiments, and as our results show, even with the naked eye, the experimental group showed a brighter fluorescence, which was backed up by measurements from fluorimeters, which you can see on the left diagram. We had to prove that this brighter fluorescence was because of our produced RNAs, not something we didn't account for. We had to conduct a reverse transcription followed by a quantitative PCR. These results did in fact show that the RNAs that caused the brighter fluorescence in the experimental group were the ones that our product amplified, thereby proving that what we made is functional in vitro. We also managed to prove that the beads, the magnetic beads, the whole system is reusable. By heating the beads which participated in a previous reaction, we found that the single-stranded DNA concentration in the solution increased, allowing us to think that the formed double-stranded DNA denatured, leaving only the single-stranded DNA bound to the magnetic beads, thereby allowing us to use these for further screenings. We realized, even though we started from wanting to help somehow cancer screening and this kind of field, we realized that by changing the sequence in the single-stranded DNA, which is complementary to the RNA we want to detect, this method could be customized to any short RNA sequence or even DNA. In order to make this easier, we even developed a software which gives you the sequences as long as you put in the RNA you want to detect. Even though this is what we achieved, there are still a lot. First and foremost, the minimal RNA concentration, which is still detectable by our device, by our product, is still undetermined. This would be the most important step that's remaining. And to altogether develop a user-friendly device, our main goal was to have something easy to use, which could be used even in a GP's office, where it's very attainable for the patients, and they don't have to go through special procedures to go through the screenings. They can screen themselves during their regular visit to their GP. I'd like to give a special thanks to the Thermos Laboratory of Szeged, where we conducted all our experiments. They really helped us, and this wouldn't have been possible without them. Also our teachers, our counselors, and the sponsors who financially supported us. Thank you. Thank you.
Tamás, thank you very much for your great presentations, and also the Academy would like to commemorate the success you could achieve, which was a very good example of what the secondary students also can achieve in this program. So I would like to ask you and also your teacher, Sándor Bán, to come to the stage to the middle, and I ask András Varró, the chairman of the curatorial board, to provide you the certificates.